Okay. All right. You ready to go, Suvrat?
Yes, whenever you say.
Okay, great. Okay, it's a pleasure to introduce Suvrat Raju, who's going to give the last talk of the conference, and it's going to be a Zoom talk, which means something, I think. So the talk is about holography of information with massive particles. Okay.
Okay, thank you very much, first of all, to the organizers. And I have to say thank you twice, because I really wanted to attend this in person, and I'm really sorry I couldn't come. And so I wanted to thank the organizers also for accommodating me and accommodating a Zoom talk. So I hope I get to visit Florence the next time, which is a beautiful city, and I'm really sorry I'm missing everything. So I'm going to speak today about holography of information with massive particles. This is in fact about a paper that appeared yesterday with these three collaborators, Alok Ladha from the Chennai Mathematical Institute, Pushkal Srivastav and Siddharth Prabhu from TIFR. And this is a follow-up on some work that we reported on a couple of years ago, and I'll try and explain that. So this talk is mainly going to describe a novel asymptotic limit for massive fields in four-dimensional flat space. Now, what we are doing is somewhat unusual, and so I have to explain why I'm trying to touch my nose the wrong way around. And so I'm going to spend some time also explaining the motivation. And the motivation for the study was originally to understand holography in flat space better. But the formalism that I'm about to present is more general. And in fact, most of this talk will be about non-gravitational theories. So, even if you don't agree with our motivation for holography, this is formalism that might be of general interest. So let me start, nevertheless, by giving you about maybe 10 or 15 minutes of motivation, just to explain why this is an interesting problem, or why it is that one should seek to do this, okay? Or at least why we thought it was an interesting problem. So the general story that this is part of is what we call the principle of holography of information, which is the idea that in quantum gravity, information that's present anywhere in the bulk is also available near the boundary. But moreover, we would like to claim that this is a property that's implicit in rather robust and basic properties of gravity and quantum mechanics. So, of course, we understand one example of this very well, which we've studied for many years, which is just ADS-CFT. But we would like to claim that this is a general property which one can demonstrate and doesn't need to conjecture in other geometries as well, or at least in some geometries where we understand it well. So the idea is that, if there is some classical or quantum information in the bulk, so here we have some set of bits, then there is some set of measurements which an observer near the boundary of the slice can do to recover that information on the same Cauchy slice, so without waiting for the information to emerge. Now, this is something which is interesting, and even though we have an example of this in ADS-CFT, it's very counterintuitive. So I just want to emphasize, the implications of this. One of the implications of this sort of a proposal is that one doesn't have split states in gravity. So in particular, in a non-gravitational quantum field theory, it is possible to set up a state of the system. This is just a question of initial states of the system, so that they look exactly like the vacuum outside some bounded region, and they have some excitation inside the region. And what is more, it is possible in a non-gravitational theory to change the form of this excitation inside while leaving the outside looking exactly like the vacuum. So that's just a property which we take for granted. And if you take what I said previously seriously, then this would suggest that in a theory of gravity, first of all, one cannot even set up this kind of a configuration, in that if one sets up an excitation in some region, one has to have tails that go all the way out to infinity. Now, this itself is not so surprising, because this is a property also of the classical theory. If you set up some mass, you have to have a gravitational field that extends to infinity. But the stronger statement is that if one changes the form of this excitation, so, in the classical theory, there's a Birkhoff theorem that tells you can have various spherically symmetric mass distributions inside. You can change the distribution of the mass inside and keep the the state outside the same, but the claim is that in the quantum theory, if one changes the form of the excitation, one also necessarily changes the form of observables outside. And so that's a surprising statement, and that's what the principle of holography of information would suggest. Now, this talk is not going to be about black holes, but I just want to emphasize that this is also interesting because it's relevant for how we understand the physics of black holes. In particular, if one looks at how paradoxes or the information paradox about black holes is formulated, it assumes that you have a classical Penrose diagram where you have some matter which fell in. And after the matter fell in, the idea is that the horizon is information free, which is true by the no-hair theorem. And moreover, the idea is that we draw a Cauchy slice and the Hilbert space factorizes into inside and outside, and therefore the observer outside can trace over the inside and obtain a mixed state. But if what I was saying was correct, what I described previously, then of course this implies that it's not true that the horizon is information free. And in fact, the information of the infalling matter is available at the horizon. And this provides therefore insight into how the information gets out of the black hole, and implies that the no-hair theorem does not hold when quantum effects are included. Okay, so these are words, but there's a precise result one can demonstrate in four-dimensional flat space-time. And that's something that we showed with, again, with Alok, Siddharth, and Pushkal a couple of years ago. So I'm going to spend a little bit of time reviewing this old paper from 2020, just to explain, why it is that we did, we are interested in massive particles. So the result that we had 2 years ago was the following. Consider some four-dimensional asymptotically flat space-time, and imagine that we have a state at least where only massless particles have been excited. So even if there are other particles in the theory, we imagine we have a state where only massless particles have been excited. Then for massless particles, Cry plus serves as a limit of Cauchy slices. And the result was that all the information about the state is present near the past boundary of future null infinity, which is in this little red region. And there is a similar result for information being present on the future boundary of past null infinity, which is this little orange region. But I'll keep talking only about future null infinity. Okay, let me just explain that in some more detail. So the idea is that both gravitational and massless matter fields have 1 over r tails as one approaches null infinity. So if one looks at the metric, there is some leading term. The leading term is just the metric of Minkowski space. And even in the theory of quantum gravity, we demand that the leading metric at infinity not fluctuate. And then there are some sub-leading terms. But the subleading terms are down by a factor of 1 over r from the leading terms. And these subleading terms contain information about the dynamical gravitons. So this object CAB, which tells you the metric on the celestial sphere, is called the Bondi shear. And its derivative is called the Bondi news. This quantity is called the Bondi mass. And similarly, there are other subleading terms. If you had scalar fields, which is what I'll focus a lot of the rest of the talk on, then if you had a massless scalar field where the mass was 0 by some symmetry or something else, then the massless scalar field would also have a 1 over r tail as one goes to null infinity. And the leading part of this tail is some function of the retarded time, which defines some observable on future null infinity. So a complete specification, if you just think of a non-gravitational theory in four-dimensional flat space, we could still describe physics at future null infinity. In fact, that is what the S matrix does for us. So the states at future null infinity are all the out states. And if one wanted to specify the state of the theory completely, one would need these observables that I described previously, the subleading terms of the metric and of scalar fields and of other matter massless fields if there are there. And one would need correlators at all possible values of the retarded time. So U here is a coordinate along future null infinity, which is the retarded time. And if I give you a state and I tell you all these correlators for all values of U from minus infinity to infinity, then that is sufficient. In fact, that is necessary to specify a state psi. I can't give you correlators for only retarded time up to 0. That would not be sufficient to specify the state in a non-gravitational theory. Our result was that in a gravitational theory, if you give correlators only for this restricted range of retarded time, which is from -infinity to -1/epsilon, this is sufficient to specify the state psi. So this is a realization of the principle that I described previously, which is that information that is present anywhere on the bulk, i.e. correlation functions involving arbitrary values of retarded time, can in fact be described near the boundary of this slice, which in this case happens to be this little red region, which corresponds to values of retarded time, which are very large and negative. Okay. Now, this relies on some very weak assumptions about the low energy theory, and I'll run through the proof quickly to explain, what it is that we did and how we missed, and what are the extensions we needed to add to this result. Okay. So let me just try and explain how this result comes about. So this result comes about as follows. So imagine that we look at the standard Hilbert space, which is obtained by asymptotic quantization. These are fancy words, but this is just the space that in quantum field theory textbooks is called the out Hilbert space. Okay? That Hilbert space is taken by looking at observables on null infinity and smearing them like with this green wave or this blue wave on all of null infinity. So you take the set of you take the vacuum of the full theory, you take the set of all observables, you smear them with all possible smearing functions, you act on the vacuum, you get a Fock space. That Fock space is the Hilbert space that we work in. Now, we want to probe this Hilbert space using a restricted subalgebra, not using the same algebra. Of course, if you use this algebra, you could detect any state within the Hilbert space. We want to use a restricted subalgebra, which corresponds to the algebra in this little red region, which is just the products of these observables in the region retarded time -infinity to -1/epsilon. Okay. So now the way this proof goes, the argument is the result is going to be that we can detect any element of this Hilbert space unambiguously using an element of this algebra. And the argument goes as follows. There are two steps to it. The first step, it only uses the fact that the energy is positive. And so in fact, it works in any non-gravitational theory as well. So all of this slide would be true with or without gravity. The argument is that if you take any element which is part of this big Hilbert space, I described it as being formed by an action of a smeared operator over all of null infinity acting on the vacuum. But in fact, you can show that you can approximate any element of the Hilbert space arbitrarily well by using an element of this subalgebra, which is in the region -infinity to -1/epsilon and acting on the vacuum. This is a version of the Riechlider theorem at null infinity. And the proof goes just the way the Riechlider theorem proof goes, which is just that imagine there was some state you couldn't form in this way, which was orthogonal to all states you could form from the subalgebra. That would be the statement that this matrix element, where this putative orthogonal state lives, is 0 for whenever these insertions are in the retarded time -infinity to -1/epsilon. But you can show just using the positivity of energy that this correlation function is analytic when these linear combinations of these variables are extended in the upper half plane. So if this correlation function vanishes for ui in this retarded time, it must vanish for all ui. But that cannot be because by assumption, the state was something which was formed by smearing these observables over all of null infinity and acting on the vacuum. And so there's no state which is orthogonal to the action of these operators on the vacuum for all values of the retarded time. And therefore, there is no such state at all that cannot be written in the form of an action of an element of this subalgebra acting on the vacuum. Okay, this is standard. This would work even for non-gravitational theories. I emphasize this is not the new element. The new element is in gravity is simply the fact that the projector onto the vacuum is an is an element of this subalgebra. And this, in fact, follows just from the Gauss law. It follows from the fact that the ADM mass is defined at infinity. And because the ADM mass is and that's true just by the familiar Gauss law, it's a limit in particular of this Bondi mass as the retarded time goes to -infinity. You can, in fact, smear the Bondi mass over some large range of retarded time and then take the limit as you goes to -infinity. And when you measure the Hamiltonian in quantum mechanics, the rule is that you get various results which depend on the spectral projectors of this operator that you're measuring. One such spectral projector is the projector on the vacuum. And therefore, in a theory of gravity, and only in a theory of gravity, this operator is also an element of this algebra near the past boundary of future null infinity. Okay, so now you see any operator can be written, I mean, just by expanding in a complete basis of states, any operator that maps the space of massless particles back to itself can be, of course, written in a complete basis. And just by using this Riech-Leader theorem, you would reach this form, which is that the operator can be written as the action of some element of the subalgebra acting on the vacuum, another element of the subalgebra acting on the vacuum. The special thing in gravity is that this projector on the vacuum that arises in the middle is an element of the subalgebra. And therefore, this entire expression is just a linear combination of a product of elements of the algebra. And therefore, the entire expression is an element of the algebra. This tells you that any operator that takes you from the space of massless particles back to itself can be approximated arbitrarily well by an operator near the past boundary of future null infinity in a theory of gravity. Sorry, by the way, I wanted to add that if there are questions, I probably can't hear. So if you want to ask something, please just interrupt me and I'll be happy to answer questions in the talk as well. Okay.
Suvrat, I do have a question. So you're being a little bit cavalier about limits here. Yeah, in what sense is this an algebra? Is it a von Neumann algebra? Is it C-star algebra? What's the
okay?
What are these things closed under? And yeah,
you're right. I'm using these polynomial algebras. I could be more precise by putting them inside bounded functions and then considering only bounded functions of smeared operators. So we could do that, and that would give us a von Neumann algebra. I mean, P0, of course, is a bounded function. These algebras, the way I define these operators is by just taking products of fields, which is an okay thing to do because at null infinity these fields are free, so you don't have to worry about. But you could smear them and put them inside bounded functions if you wanted to be mathematically very precise.
Yeah, it's just like, yeah. I feel like you might need to be mathematically precise for this kind of argument. It seems like
so the
it's
argument
a delicate argument to make sure that, yeah. Okay, so
yeah, I mean, we could discuss if you have specific reservations, but the part where I needed it was the Riech-Leader theorem, which of course, so you're right that we could, where I described this algebra here, I should have integrated it with a small spherical function and then put it inside a bounded function. But I don't see anything. I don't see any obstruction arising from that. But I'd be happy to talk more if there are.
I don't know specifically, but for example, xn typically the norm of that operator will diverge. So
correct.
I don't know whether that's a problem or not. It may not be, but I feel like it seems like it should be. Yeah, I would like to see the epsilons and deltas of this because it might be.
Yeah, we can. Yeah. So, this is a question of whether the Riech-Leader theorem is valid in general. So this, this part of the, if you had a concern about this part, this is the part that's special to gravity. This is just an extension of the Riech-Leader theorem to infinity, but we can discuss.
No, I have no problem with that. Just like when you apply it outside of that regime, yeah, I want to see, because, the Riech-Leader has the epsilons and deltas, and so I have no problem. But yeah, so I don't really have something specific to poke at, but I think I would like to see the.
Okay, sure. Yeah, I'd be happy to talk more. But remember, we are always acting on the vacuum with this. So it's not, you're right. This is an operator which, in principle, has unbounded norm. But we can talk more if something specific. Fine. Okay. In any case, this was the older result. So the result was that I can squeeze these observations that go over all of null infinity to observations in this little band. And that was a statement alternately stated that operators that map you from one state to another state in the space of massless particles can be found near the past boundary of future null infinity, where this state, most importantly, was obtained by acting with these smeared operators on all of null infinity on the vacuum. But the point is that states of massive particles are not of this form. You can act on null infinity all that you like, but you'll never generate a state which has one massive particle. So the question is, how does one extend the result that I just presented to include massive particles? Okay, so I hope the problem is clear. I described some result. The result said that rather than making observations on all of null infinity, I could get away by making observations on the past boundary of null infinity. But observations on all of null infinity are still not sufficient to identify states of massive particles. Okay. And the reason is, of course, that as we all know, massive particles go from I minus to I plus, not from Scri minus to Scri plus. And in fact, there is a perfectly satisfactory description of massive fields which exists at time like infinity. I mean, what I said previously is not an obstacle to defining the S matrix. We define the S matrix absolutely fine in QFT textbooks. But that S matrix involves a description of massive particles in the far past and the far future, and not a null infinity. So now what could we do? Okay, one option is the following. We could say, well, all information about the theory is available on Scri plus minus, which is this red region, and I plus, which is the future infinity, or on Scri minus plus, which is the orange region, which is not displayed, and I minus. We could say that. But this doesn't quite keep with the spirit of the general program I was trying to describe at the beginning, which is that information is available on the boundary of a Cauchy slice. So future infinity and past infinity are not on the boundary of a Cauchy slice. And we would like holography to work in the sense that information in the bulk is available at the boundary, but not at the future boundary, somehow on a space-like boundary. Okay. The other option is we could say, well, we could work with just bulk observables at large R. So, instead of trying to go all the way to infinity, we just say, well, we go out to some distance. And then we say all information is available on Scri plus minus. So for massive massless particles, we go to null infinity. And then we go to bulk observables for massive particles at large R. This is, of course, unsatisfactory. I was just asked about, how to make the argument at null infinity, how to put in the epsilons and deltas there. But, in this situation, we would be in much more trouble because we couldn't even define the algebra and the bulk at large R. And that's because the bulk fluctuates in the theory of gravity. So asymptotic algebras, I would argue, make sense even in quantum gravity because they're at infinity where the field becomes coupled, but where the field becomes free. But bulk algebras are very subtle. So, speaking of bulk observables might be all right in some approximate sense, but it's not very precise. Okay, the third option is we just forget about massive particles. And, for some questions about black hole evaporation, it's true, they don't matter. So, we can discuss black holes and whether information comes out. And we can perhaps discuss it without really worrying about this issue of massive particles, because if you have a big enough black hole, it doesn't emit too many massive particles until the end of its life. And so, maybe you could say that you get almost all the information out on null infinity, and there's some you don't get, and you get that only at the end. And that's possible, and indeed it's maybe acceptable in some discussions of black holes, but it leaves us, I think, with a slightly incomplete picture of flat holography, and so we would like, this is not something which we would like either. Okay, so for this reason, now in the remainder of the talk, I'm going to describe a novel representation of massive particles on an asymptotic DS3 slice, which is at infinite proper distance from a given origin. So it's a slice of this kind. Okay, it's an infinite distance. So it's like, as you will see, for those of you who are familiar with the geometric construction of a blow-up of spatial infinity, you will see this has some similarities, but also some differences with that construction. Okay? So this, I should say ahead of time, is a unusual, perhaps somewhat ambitious construction. Maybe it doesn't even work in the end when we investigate it further, but we think it's very interesting, and it's interesting for the reason that I just tried to explain, which is that it's of interest if you really want to understand how to include massive particles in flat holography. Okay, I should also say that much of the following discussion is applicable to quantum field theories, independent of our holographic motivation. So even if you don't agree with the holographic motivation, this is still just an interesting QFT discussion, so much of what I'll say in the next, for most of the remainder of the talk is applicable to QFTs. Towards the end of the talk, I'll go back to gravity. Okay, so let me just first describe how, the geometric aspects of this. So the idea is very simple. We could do this in asymptotically flat space, but let's just discuss Minkowski space. So in Minkowski space, we introduce coordinates, which one is the proper distance, which is rho, and you just write, the usual T and R coordinates as rho sinh tau and rho cos tau. And then the metric of Minkowski space just becomes this. And so at every value of rho, which is the proper distance from some origin that you chose, you have a DS3 slice. And so slices of constant rho look like this. Okay? And slices of constant tau look like the colored ones. Okay? Now, the point is that each constant row slice is a de Sitter slice. It's a global de Sitter slice. As you can see from this part of the metric, so if you just keep the row part fixed and vary the other coordinates, which are tau and omega, you have global de Sitter. And it's convenient on global de Sitter to use embedding coordinates. The embedding coordinates are just that you embed de Sitter in an ambient 4-dimensional space. So sometimes you might see the symbol X, and the symbol X just has a simple relation in terms of tau and omega. Okay. So now the idea that is in this geometry construction to take rho goes to infinity. So if you take rho goes to infinity, you have these slices at rho, and you take rho goes to infinity, you get this red slice, which is the boundary DS3 slice, and then you rescale the metric. So the metric is just that of global DS3 with unit radius. And this is in fact very similar to what in the geometric literature is called the blow up of spatial infinity. And the reason this is called a blow up of spatial infinity is the following. Imagine that as you take this limit of rho goes to infinity, you focus on a fixed interval of tau and of omega. So on a fixed interval, say just of tau. You will find that if you focus on a fixed interval of tau, as rho becomes larger and larger, the behavior of this interval, this coordinate interval, becomes like this. So this interval, eventually, if you fix a range of tau that you're looking at, becomes simply a blow up of spatial infinity. It becomes something that interpolates between scri minus and scri plus. And that's an important thing for relativists because I naught is a singular point in the Penrose diagram. And this smoothens up I naught and gives you a nice interpolation between past null infinity and future null infinity. Now, the subtle difference in what I'm about to describe is that at times I will consider observables which are smeared over this entire DS3 slice and then take the limit as rho tends to infinity. So while it is true that if you fix the tau coordinate and take the limit as rho goes to infinity, the point that you get is necessarily space-like separated to some point in the bulk here. It's not true if you smear first and then take the limit as rho goes to infinity. So that's a subtle distinction, but between this construction that I'm describing and the blow up of spatial infinity, but otherwise it's very similar. Okay, so now let me just describe some of the physics just by thinking of a free theory. So imagine just some free massive field in Minkowski space. So you can immediately expand this in some basis of solutions. One way to expand this in a basis of solutions is just that you separate variables, and the dependence on rho is this Bessel function, and then the dependence on the other coordinates turns into that of a massive field in de Sitter space with a mass parameter that is nu. So for a single field in Minkowski space, we get an infinite number of fields in de Sitter space with a continuous range of mass parameter that goes from 0 to infinity. Okay, now you can quantize this, of course, and you can quantize, in fact, each of these de Sitter fields. The normalization is fixed by how they fit together in the big Minkowski field, but otherwise you can just quantize the de Sitter fields. And you will find that when you quantize them, the quantization that you get is as follows. You'll find, of course, that the appropriate positive and negative energy modes to use on these de Sitter slices are what are called Euclidean modes. Okay? So Euclidean modes are the modes that you get if you take de Sitter, this is my de Sitter, and continue it analytically to a sphere, to a Euclidean sphere. And if you do that, the modes that are regular on the south pole of this continued sphere are what are called Euclidean modes. And these modes, which are the correct positive energy modes or positive frequency modes in your quantization, will turn out to be these Euclidean modes in de Sitter space. So the Minkowski vacuum turns into the Euclidean de Sitter vacuum for these component fields. So there's some discussion in the literature about, what's the right vacuum to use? Should we use the Euclidean vacuum or these alpha vacuum or something else? Here we don't have a choice. If you use the Minkowski vacuum, then you should use the Euclidean vacuum for these de Sitter fields. And the Hilbert space is generated by, of course, acting with these creation operators on the Euclidean vacuum. Okay, now let me now describe this extrapolate limit. So if you go back to this expression that I had here, you see that at large rho, these modified Bessel functions, which are also called the McDonald functions, they die off exponentially. So the idea is just that you strip off the exponential tail of this function. And the interesting aspect of this fall off is that it does not depend on this parameter nu. So it's nu independent. So if you strip off this exponential tail, you would find an operator that's intrinsic to this boundary, hat I naught slice, so this boundary de Sitter slice. So the formula is just that you take the bulk field and you take this limit as rho goes to infinity, you strip off a certain exponential tail, and you get an operator that is intrinsic to this I naught, or to this boundary DS3. And this is our version of our proposal for what should be the extrapolate dictionary. So just like in ADS, we have an extrapolate dictionary, which says you strip off the leading power law. Here you strip off the leading exponential, and you get some operator that's intrinsic to the boundary, which is this operator. You can expand this operator in terms of the de Sitter component fields. In fact, it's just the integral of all the de Sitter component fields with unit measure. And you can also expand it in terms of the oscillators that I described, and you would find this expression. So you have some spherical harmonics. They're not so important. They're just telling you how things vary on the sphere. You have these Euclidean modes. You have these oscillators. And then this normalization is something that I want you to focus on. Is some factor that's fixed by the way these de Sitter component fields fit inside the Minkowski fields. And it's a factor that grows exponentially for large mass parameter in de Sitter. Okay? So this is something that is potentially a problem. And the reason it's a problem is that this exponentially growing factor, which assigns larger and larger importance to de Sitter fields with larger and larger mass parameters, might cause divergences in boundary correlators. So if you take the vacuum and you just try to evaluate a two-point function, this is undefined for x1.x2 larger than -1, and in fact it's 0 for the other domain. And the reason for this is that the large rho limit with two exponentials, so the limit with e to the twice m rho of the insertion of two fields does not exist if x1.x2 is -1. And it's pretty easy to see geometrically why it doesn't exist. The reason is, if you take a point here, I hope you can see my mouse, and another point here, and you look at the distance between them, that's not 2 rho, because these points are separated in time. It could be much smaller than 2 rho. In fact, in this limit here, it could become very small. And for that reason, this distance, because the distance between 2 points is not 2 rho, to rescale the correlator by e to the 2 rho is not a good thing to do for this kind of a pointwise insertion. Okay, the solution is pretty simple that we found. And the solution is you look at these operators, but you need to smear them. Okay? So you need to smear them over all of this boundary DS3 slice with some smearing functions like the cartoon I've shown here. So you just take, this should have been z of x, sorry, not z of g. So z of g is integral of z of x with some smearing function g of x. And you can expand this in terms of the modes that I described previously, and you would find this expression for z of g in terms of the coefficients of these modes. But the important part is that if you now take the smearing function to be such that it assigns exponentially small weight to high mass parameter fields, then you would get finite fluctuations for the z of g. So we can derive a simple consistency condition for what kind of smeared operators have good fluctuations in the vacuum. And this is one of the conditions. There are also conditions on how the behavior has to be at large L, but those are not very important. These are the important conditions. Such smearing functions are not hard to find. For instance, if you just take a Gaussian, this kind of a Gaussian does have the right properties because, going to this mode basis is roughly like taking a Fourier transform. And we're demanding that the Fourier transform die off exponentially. For a Gaussian, it dies off much faster than exponentially. And you can explicitly compute, for instance, what the two-point function of such a smeared field is. And it turns out to be some value, which is not important, but it's something that you can compute. It's finite. Okay? So alternately, one other way to think of this is that the correlators of these boundary fields are distributions, but they're distributions that don't act on, all square integrable functions, or not even on functions that die off rapidly enough, but they're distributions that act on a limited class of test functions, which are those which have a Fourier transform that dies off exponentially fast. More precisely, which are those which, when you expand in these de Sitter modes, which is morally a Fourier transform, has coefficients that die off exponentially fast. Okay? So this is a subtlety, which in fact is a subtlety that bothered us a lot when we found this, but we think this is the answer, at least in the free theory. Okay, now we can do something nice once we have this understanding. For instance, we can do the analog of what is called the HKLL construction in ADS-CFT. So as all of you know, the HKLL construction involves smearing operators over the boundary and obtaining operators in the bulk. We can do that here as well. The reason we can do that is that this boundary DS3 slice you see at any value of rho is causally connected to an entire Cauchy slice in the bulk. And therefore, by choosing an appropriate smearing function, which is this kappa, you can write any local bulk operator in terms of the boundary operators. So we have some infinite sum expression for this kappa, but in some cases, we can evaluate it explicitly. One such case, which gives us a very nice formula, is a spherically symmetric case, where you take the bulk field and you just integrate it on a sphere, so you can focus on the L equal to 0 mode. In that case, the smearing function takes on this very nice form, which is roughly e to the minus m rho naught. Rho naught is the position of this bulk field times cosh of tau naught minus tau. So tau naught is the time coordinate of the bulk field, or the de Sitter time coordinate of the bulk field, and tau is the coordinate in the boundary. So there's a nice smearing function that you can write down that allows you to reconstruct all local bulk operators. Let me draw your attention to this doubly exponential fall off with de Sitter time, which will be important also in the next slide. Okay, so in fact, there's a general rule that tells you about the decay of smearing functions and the localization of the bulk field. The general rule is that if you consider functions that die off doubly exponentially faster than e to the 1 over delta cosh tau, that means that you take e to the delta cosh tau and multiply it with g, and you take the limit as tau tends to plus or minus infinity, and it goes to 0. So that means that g itself dies off faster than e to the minus delta cosh tau. Then you can show that if you use this g as a smearing function, if you take a boundary field and you smear it with this g of tau, so you take a narrow smearing function, then this field commutes with all operators in a radius rho naught, where rho naught is 1 over twice m delta. Okay. So here's a cartoon that shows this. You take a smearing function in the boundary that has some width in cosh tau of delta, and you necessarily find an operator that's outside of a large ball in the bulk that's localized in this pink region here, because it commutes with all operators in the blue region. And this is a general result that we can prove, and I'll come back to this result at the end. Okay, another question one could ask is, how do these things behave under the asymptotic symmetry group? We have not answered that question completely, but the first thing you could worry about is just translations, and that's because by choosing this origin and this coordinate system, we broke translational invariance. And in fact, it turns out that these operators behave in a very nice way under translations. If you translate with some space-time parameter y, it's just like multiplying the operator with e to the minus m into y dot x, where x is the position of this operator. Okay. Of course, this is this factor itself grows doubly exponentially. So one is not permitted to use this formula if this entire smearing function does not die off appropriately at asymptotic tau. But provided it does, there's a simple and general formula for the transformation of these operators. It would be interesting to understand more general transformation properties under the asymptotic symmetry group. Okay, let me say some things about the interacting theory. I said everything I said so far. Some of the results I described previously, such as the result about localization and also the translations, is valid also in the interacting theory. But let me just spend a few minutes justifying why this whole thing makes sense also in the interacting theory. And the reason is as follows. It's an LSZ kind of argument. Okay? So imagine that you have some interactions and you're trying to compute the insertion of some field at large rho. So the way you would compute it in perturbation theory is at least by some Feynman diagrams that connect this point rho to the rest of the diagram, and then you have some other big diagram that involves the other insertions. Now the main point is that this propagator that connects the external point to the internal point of the Feynman diagram, you expect on very general grounds to have some spectral decomposition of this kind in terms of free field propagators. Now, this is also important because it tells you that in the interacting theory, you might want to do field redefinitions. There's no sense in talking of the field phi, and it's okay as long as you use any field which has the right spectral decomposition. And if the spectral function has the property that it has a delta function at the value of the mass, which is now the renormalized mass, then you see that the fall off of this entire Feynman diagram is controlled by the fall off of the lowest value for which the spectral function has support. And that's because each free field propagator has a fall off that's controlled by e to the minus s rho, where s is the mass. And so the leading fall off is the smallest value of the mass. And therefore, in perturbation theory, you expect that this entire correlation function has a good limit, provided you have a stable massive particle. Okay, so the spectral function has a delta function and then has whatever it has beyond that. So in particular, you can work out this extrapolate limit, and you'll find some expression in terms of Gegenbauer polynomials. That's not important. The only subtlety, and in fact, this is a subtlety that we have not addressed in our paper yesterday, is that this extrapolate limit in the interacting theory has the same e to the pi nu by 2 growth that I emphasized in the free theory. It has the same growing importance assigned to fields of larger de Sitter mass. And we expect that just as in the free theory, provided you smear this with the right class of test functions, you can get rid of this or you can cure this. But in fact, we do not yet have a concrete proof for all cases, and that's something that is missing in the analysis that I'm about to present. Okay, let me just say one more thing about interactions. I just want, it's not true that the interacting theory is a sum of a bunch of interacting theories in de Sitter space. Okay? So in the free field theory, in fact, the Lagrangian is the sum of the Lagrangians for the constituent fields, these de Sitter fields. So it really looks like the sum of different, theories with de Sitter theories. But generally, interactions induce various couplings between these de Sitter masses. So the final theory you have on the boundary is not just a sum of independent interacting de Sitter theories, but rather it's some theory which has all sorts of couplings between these different de Sitter mass parameters. You can work out some of these couplings sometimes explicitly. For instance, if you take a phi cubed interaction in the bulk, you will find that the couplings in the boundary are controlled by what's called the Apple F4 function. This is the first time, I promised you, I encountered this function as well. But it's in any case, it's an expression that you can evaluate for how this works. And it's an expression that Mathematica cannot evaluate, but one can evaluate using old Russian textbooks for what this interaction does in the boundary. Okay, good. So now let me return to the theory of gravity and spend maybe five minutes talking about gravity. And then I'll stop. Are there any questions at this point that I should take?
No, it doesn't seem. Yep.
Okay, thank you. Okay, so let me try and now make a conjecture about how holography should work in the presence of gravity. Okay, this is a conjecture because, as I said, we do not understand the interacting algebra very well, and we are worried about these divergences that might occur at large nu. But let me tell you how we think things should work. And as I said, it's a conjecture. So what we want to do is we want to consider the algebra of boundary operators with smearing functions that die off exponentially fast. Okay? Remember, I told you that if you look at smearing functions that die off at least this fast, they're smearing functions that are in a non-gravitational theory in the exterior of a ball with radius 1 over twice m delta. Okay? So in a non-gravitational theory, this algebra corresponds to operators outside a large ball. But because this is an asymptotic algebra, right? So because this is not some bulk algebra we are talking about, because this is an asymptotic algebra, we expect that this algebra makes sense also in a gravitational theory. I mean, that's the whole reason to try and focus on asymptotic algebras, because we can then compare the properties of this algebra in the non-gravitational theory with the algebra in the gravitational theory. Right? So this algebra in the non-gravitational theory corresponds to operators outside a large ball, so in this pink region. Now, in a gravitational theory, we claim that we look at the algebra of operators in the past boundary of future null infinity and the algebra of operators that on this blow up of spatial infinity or this boundary de Sitter slice has an exponentially large fall off. This is a cartoon of how it looks like. It looks like, this red region and this green band, if you can see it. Alternately, you could take the orange region, which is the future boundary of past null infinity, and take the algebra of that and operate massive operators on this green band. But, as I said, let me focus on future null infinity. So you look at the algebra of operators on future null infinity, past boundary of future null infinity, times the algebra of operators that are smeared in a particular way on this boundary de Sitter slice. In a non-gravitational theory, this algebra lacks information about a large ball in the bulk. You can see this, in fact, from this figure. If you imagine the bulk being inside this cone, then you see that the algebra of future null infinity near the past boundary lacks information about what's space-like separated to it. If you acted with a unitary that was space-like separated, then that would commute with everything here. Similarly, this green region on this boundary de Sitter slice, as I said, in the non-gravitational theory, corresponds to operators in the exterior of a large ball. The conjecture is that in the gravitational theory, this has all information. And the argument, in fact, goes in precisely the same way. You can prove that even though you look at the algebra of operators, with these rapidly dying off smearing functions, you can prove a Riesz-Leiter theorem for these operators, which tells you that any state can be generated by the action of these operators on the vacuum. And of course, just as previously, the projector on the vacuum is an element of this boundary algebra because that anyway lives on the past boundary of future null infinity. That's just the ADM mass. And therefore, as previously, any operator which maps you from one state to another state can be written as the action of an operator from the subalgebra on the vacuum. But this whole thing is now an element of the algebra because the projector on the vacuum is an element of the algebra. Okay. I should emphasize that, sorry, before I say that, so the result is once again that, these observables which lack information in a non-gravitational theory are complete in a gravitational theory. So it's very similar to the result that we had on null infinity, except that it now includes also massive particles. But I should emphasize that this result is a little more ambitious than what I told you about massless particles earlier. And that's because it's subject to these potential divergences that come from this exponentially growing factor of nu that I showed you previously. You can think of them as IR divergences. And it's subject to potential, the fact that we can cure these potential divergences in interacting correlators. And as I said, we do not understand them completely. And it's possible that, maybe there's no solution to this, in which case this entire program doesn't work. Although we don't have any signs that there's no solution, it looks to us that we should be able to cure these divergences with appropriate smearing. But I should emphasize, or I should state the caveat that whatever I said about gravitational theories, interacting theories, is subject to a better understanding of these potential IR divergences. Okay, so I'm done. Let me just summarize, and then I'll stop. I said that the motivation for this talk was a general proposal, which was that in quantum gravity, the information that is present on the bulk of a Cauchy slice is also available on its boundary. So this is the cartoon. You have some information in the middle. There's some observations you can do at infinity that can extract that information. This is not a violation of causality. It's, sometimes people ask, how does the information jump from here to here? This is a statement of how states can be prepared. It's a statement that the only way to prepare a state or put this information inside is by satisfying the constraints in such a way that the information is also available outside. One realization of this result I presented was in future null infinity, which is that information on all the Cauchy slice was available near its past boundary. I think this is this provides insight into why gravitational theories are holographic. Why is it that gravitational theories are holographic and non-gravitational theories are not? I think this is the reason that that's the case. I think it's also important for understanding paradoxes about black holes, because those paradoxes presume that you can put information inside a black hole without it being available outside. This principle is something that can be made precise. It can be proved, although I described the proof in flat space, it can of course be proved in ADS, although we already know the result there from ADS CFT. But there's a challenge in flat space to include massive particles in this framework. And the challenge is that massive particles, the conventional asymptotic description, involves particles at past infinity and future infinity, but those don't fit in this general program of information being available on the boundary of a Cauchy slice. And so for this reason, our idea was to try and do this construction of looking at de Sitter slices at rho and going to infinite rho, and looking at the de Sitter slice at infinitely large rho. And we propose that that one should strip off the exponential tail of massive fields and obtain some operators that are intrinsic to this boundary de Sitter slice. This boundary algebra is a subtle algebra. It's a subtle algebra because when you take this boundary limit, you get potential infrared divergences. But it's a very interesting algebra. We can derive many interesting results. We can derive some version of HKLL. We can derive general properties of what kind of boundary operators are localized where. We can understand how interactions are encoded on the boundary and so on. And in a theory of gravity, we conjecture that all observables can be obtained with a subset of operators on this algebra and massless operators near the past boundary of future null infinity. But this is still a conjecture at this stage. So let me stop here and thank you for your attention.
Thanks, Suvrat. Are there further questions for Suvrat?
Oh, hi, thanks for the very nice talk. I was just wondering, are these sorts of constructions, I guess, even in the massless case, possible when the bulk is non-static?
Oh, I don't think it matters if the bulk. I don't think we assume that the bulk is static. We need to assume that the bulk is asymptotically flat. So if the bulk is asymptotically flat, because this construction eventually only makes a reference to the asymptotic properties of the bulk. So we wanted to define some extrapolate dictionary that goes out to infinity and then looks at the tails of the fields at infinity and then define some observables that are intrinsic to infinity. So it's true that in some of what I presented in the beginning, I assumed a globally Minkowski space, but in the end, all we need is the fact that it should be asymptotically flat. So you could have all kinds of things happening in the bulk. I mean, otherwise we would exclude all interesting states. So we want to include interesting states, including things where there is dynamics in the bulk, but we do demand that it should be asymptotically flat.
Oh, okay. So even in the non-static case, it's possible to have this sort of Riesz-Schlieder theorem on the asymptotic boundary. You can find this positive operator and.
For the case of massless particles, for sure. I mean, the states that I was looking at were not static states. I mean, there was nothing which was time independent, right? So remember the Riesz-Schlieder theorem that I proved. Maybe I should share screen once more. The Riesz-Schlieder theorem involved the action of operators on the vacuum. So maybe I think I understand your question better. Yeah, I proved that any state can be approximated arbitrarily well by the action of an algebra on the vacuum. Now, this state here is the vacuum. This state here is not an excited state, right? This state here is the vacuum. Now, the reason this is interesting in gravity is that in a full theory, you can write any state in this form, right? So any operator in this form. And so the only place I used the Riesz-Schlieder theorem was here. Now you're right that this state here is a static state, right? But that's okay because what I wanted to do was substitute this with the projector on the vacuum, which is here. So I think your question was, can you prove a Riesz-Schlieder theorem for arbitrary states? No, you can't. But we don't need to prove the Riesz-Schlieder theorem for arbitrary states. You're right, you could take states which have unbounded energy and then you wouldn't be able to prove the Riesz-Schlieder theorem, but we don't need to. And that's because we only need, the Riesz-Schlieder theorem is the standard Riesz-Schlieder theorem, that the action of a subalgebra on the vacuum gives you all states. And the part about gravity is that the projector on the vacuum exists at the boundary. So I think does that answer your question?
Yes, yeah, thank you very much.
Thank you.
More questions for Suvrat? Yeah.
Let's say that I start from the algebra, which is defined a bit above respect to Scri plus minus.
Yes.
This should contain the algebras at later times, but not the one at earlier time, right?
Correct.
Is this possible to reconstruct part of the space-time from that algebra? Like an analog of subregion duality?
So right. Okay, that's a good question. So here, what we would, you're right, that was here. So, to ask a question about subregion duality, let me just erase this. what we would like to do is consider algebras on part of the celestial sphere. So here I didn't take the celestial sphere at all. You know, subregion duality is always, what if you take a part of the boundary? So here I always had the celestial sphere sitting, I'm so good at drawing. One second, let me try and draw better. Right, so I had a sphere that was going around, and when I said I restricted the retarded time, I didn't say anything about the sphere. I allowed myself tacitly to use all values of the sphere coordinate. I think it's, so indeed one could ask, you know, what if we restrict to some values of the sphere coordinate? What part of the bulk can we reconstruct? That's a very interesting question. I don't actually know the answer to that in detail. It's a very interesting question, but it's not one we have explored. What we have right now is some version of what happens if you include the full celestial sphere at null infinity. But you're right, it's of great interest to ask. What if you assume, what if you take part of the celestial sphere at infinity? What can you see in the bulk? It's a very interesting question, but I don't know the answer.
Okay, thanks.
Further questions? If not, let's thank Suvrat again.